Welcome to This Explainer. When we think of artificial intelligence, we usually picture these sleek, ethereal lines of code just floating around in a digital void. But today, we're going to look right past that software layer to map out the massive, intensely physical, heavy metal supercycle that's actually driving the global economy right now. So let me start off by posing a bit of a paradox for you. When you interact with a massive large language model, it honestly feels like magic, right? It's instantaneous. But what if the biggest barrier to the actual future of AI isn't the software, or the algorithms, or the code at all? What if the true gating factors, the things that could actually slow this all down, are literally copper wire, pouring concrete, and the physical capacity of your local power grid? For years, the tech industry has been completely focused on the ethereal nature of the cloud. This idea that everything just operates seamlessly in the background. But the sheer scale of modern AI has forced a pretty violent return to physical reality. To run these models, the cloud has to connect to the ground. We are literally talking about millions of miles of copper wire, massive nuclear power plants, and towering high-voltage transmission grids. Now, why does this matter to you? Well, it comes down to a staggering figure, $725 billion. That is the projected 2026 capital expenditure by the major hyperscalers, and it's flowing almost entirely into physical data center infrastructure. Understanding this physical supercycle shows you exactly where arguably the most significant capital in human history is going right now, and exactly who stands to actually build it. Okay, so let's dive right into this. We're going to structure our deep dive today around three logical pillars. Pillar 1, the brains. Pillar 2, the power. And Pillar 3, the builders. All right, let's kick things off with Pillar 1, the brains, focusing on silicon and networking. We're starting at the very core of the AI ecosystem here. Because, frankly, before we can even talk about the grid or the people pouring the concrete, we have to understand the specific silicon that's demanding all of this energy in the first place. Before we get into the crazy market dynamics, let's quickly define a key term you're going to hear a lot. What exactly is an XPU? Well, it's really just a general term for custom accelerators that are designed specifically for AI training and inference workloads. General-purpose GPUs have gotten us incredibly far, for sure, but major hyperscalers are now heavily customizing their silicon. They're creating XPUs that are hard-coded for their specific models just to gain every single edge they can in efficiency. And honestly, just as important as the computing itself is the networking. Enter SerDes, or serializer/deserializer interfaces. This is the underlying tech enabling ultra-high-speed data transfers across massive infrastructure clusters. Think about it. You can have the absolute fastest XPU in the world, but if you can't move that data across tens of thousands of chips basically instantly, your billion-dollar data center is essentially just a giant brick. To give you an idea of the sheer scale of the silicon shift, Broadcom recently announced they have a clear line of sight to achieve AI semiconductor revenue of over $100 billion by 2027. $100 billion. That growth is being driven by deep, multi-year engagements with massive players. Think Google, Meta, Anthropic, OpenAI, who are all desperately scaling up deployments across literally gigawatts of compute capacity. And this brilliantly illustrates a crucial physical reality about how these systems are built. When clustering all these XPUs within a single server rack, Broadcom is pushing hard to keep customers on direct attached copper rather than switching immediately to fancy optical transceivers. Why? Simply because copper provides the absolute lowest latency, the lowest power consumption, and the lowest cost. Optics are fantastic for scaling out across a massive building, but for scaling up within a single dense cluster, copper is literally king. So the main takeaway for our first pillar is pretty clear. Compute hardware is no longer a one-size-fits-all game. It is shifting aggressively from general-purpose GPUs to highly customized XPUs, and they're being supported by massive internal copper networking just to optimize every single solitary watt of power. Moving right along to Pillar 2, the power, or as I like to call it, the gating bottleneck. So tracking our progress, we've moved outward from the compute layer, and now we're looking at the energy layer. Power is no longer just some downstream dependency that gets figured out later. It is the absolute first design question developers have to solve today. Now, what's really telling about this situation is a massive 76% surge. That is exactly how much wholesale power prices jumped across the PJM East Coast grid in early 2026. This was driven by a nearly 400% surge in capacity costs. Why? Simply because this incredibly concentrated data center demand is colliding violently with our aging grid infrastructure. Because traditional tech hubs, places like Northern Virginia, are functionally tapped out right now. Hyperscalers are literally scouring the country for power. Take Project Jupiter, for example, a massive data center campus down in Doña Ana County, New Mexico. As Lanham Napier of Borderplex notes, this desperate search for power is literally redrawing the industrial map of the United States. It's bringing unprecedented infrastructure investment to entirely new regions. But, perhaps the absolute most incredible example of this energy desperation is the revival of the 3 Mile Island nuclear facility by Microsoft and Constellation Energy. This deal secures 835 megawatts of constant-on baseload power, completely bypassing the massive multi-year delays of utility grid upgrades. And fascinatingly, they are actually retaining the 1970s analog control systems. It turns out that having a bunch of physical dials and switches provides an air-gapped level of cybersecurity that modern, deeply connected digital networks simply cannot match. It's wild. The practical takeaway here is really profound. In the AI race today, energy efficiency and guaranteed off-grid power access are now primary competitive advantages. Power generation completely dictates who gets to build the biggest models. Bottom line, if you don't have the power, you don't have the AI. Which brings us to Pillar 3, the builders, focusing on physical execution. This is the final step in our sequence. We have the custom chips, we have secured the power, and now we have to look at the physical execution. The actual construction, the stringing of transmission lines, and the heavy industrial manufacturing that connects this whole system together. To really understand the scale of this physical build-out, just look at Quanta Services. They are a primary builder of high-voltage transmission networks, and they recently reported a staggering backlog of $48.5 billion. That is just an enormous volume of high-voltage transmission and utility interconnection work demanded by the market right now. Their craft labor platform is quite literally the physical muscle making the AI supercycle possible. Similarly, traditional industrial electrical manufacturers are just getting swept up in this massive wave. Powell Industries, a company traditionally known for heavy industrial switchgear, is now securing data center mega projects. You see, you need massive, highly specialized switchgear to safely manage these unprecedented gigawatt-scale electrical loads. Without these heavy, very physical components, the data center simply cannot function safely. Which naturally leads us to our final takeaway. Blue-collar craft labor and heavy industrial engineering are the true, real-world gating factors for deploying AI at scale. Without the linemen, without the electricians, and without the switchgear manufacturers, the digital cloud simply cannot expand, period. So the crucial point to remember is this. The AI infrastructure stack is deeply physically integrated. Silicon is shifting to highly custom XPUs, power availability is entirely dictating exactly where growth happens, and blue-collar builders control the ultimate pace of the deployment. In a previous explainer, we talked about how software ate the world, but today, as you can see, we are seeing exactly how the physical world is biting back. But I want to leave you with one final, truly provocative thought. We're currently seeing platforms like NVIDIA's GR00N foundation model and Tesla's Optimus humanoid robots successfully merging these massive AI brains with physical robotic bodies. If the gating factor to AI expansion right now is physical human labor, are we rapidly approaching the von Neumann moment, the exact point in time where artificial intelligence finally gains the physical capability to mine its own copper, pour its own concrete, and literally build copies of itself? That, right there, is the ultimate convergence of the cloud and the ground. Thank you so much for joining me for this explainer, and I will see you in the next one.